Okay, Frode, we are capturing. You can start. You are mute, Vinicius.
Oops. Yeah, now I'll go. Thanks. So again, sorry everyone for this. For not keeping up with time, but we have some issues with the connections. But I will again thank you very much for everyone participation and for this morning session before eCalc sessions. I'd like to go directly to introduce Frode, and thanks again, Frode, for accepting our invitation to this Introduce to eCalc course. So Frode is a specialist in reservoir technology at Equinor in Norway, where he has been working since 2005. Prior to joining Equinor, he has worked as a consultant at Lab Optimization in Sweden. He completed his master's and PhD in engineering cybernetics at the NTNU, the Norwegian University of Science and Technology, where he also worked as a postdoc from 2002 to 2003. Frode has worked as a principal engineer in reservoir technology and hydro in Osga fields, and he has extensive experience in reservoir technology, well planning, modeling, history matching of reservoir simulation models. Currently, Frode is working on energy efficient drainage strategies at Equinor, where he aims to reduce emissions by simultaneously working on the drainage strategy and in the installation facilities. He is also teaching frequent internal courses and occasionally for selected external groups, just like our group. So again, we're very privileged and happy to be receiving or having this opportunity to have the course from teach by Frode for eCalc and NAPKIC short course. Thank you very, very much again, Frode, for your time. And please, the floor is now yours. I will stop sharing my screen.
Thank you, Vinicius. Again, very sorry for the delay, technicalities. Vinicius, I hope that you can help me with time here now. I don't know how long we can go on for today. I can stay, but I guess you have a schedule. Try not to rush this anyway, though. eCalc, it's a software developed in-house in Equinor, but it's open source. We use it for calculation of energy demand and greenhouse gas emissions from oil and gas production and processing. So this is implemented throughout in Equinor. Developments started late 2017, so I joined the project in 2018. My side of it has mainly been on setting it up for all the offshore installations we have in Norway and helping users using it. I'm also interacting with the development side of the project where our software engineers are working. So I'll try to sort of divide the talk into sections here. These slides that look like this is sort of a section divider. I start with the motivation. So why do we do forecasting of emissions? What about multidisciplinarity and the software itself? We'll try to, at least the original plan was to talk for 45 minutes, have a break, some questions, coffee, and then we'll continue with the second lesson after the break. Like a 15-minute break is what we're looking at here. So this is a slide from the company Equinor. Like many other oil companies, they have established ambitions to become a net zero company or in some sense reduce their emissions in some years ahead. For Equinor, that's around the year 2050. But on the way there, they are having emission goals in 2030 also, and they are not relative, they are absolute emissions. But they're measured as a 50% reduction towards a level in an earlier year. So to achieve You can see we are around here in time now, around 2023, and we are only like 7 years ahead, 6 years ahead. We are going to have 50% of our scope 1 and scope 2 operated emissions, base year 2015. That's the goal. Many companies have similar goals. But to be able to achieve these goals, you have to have a way of working. Somebody could mute, please. In the way that we work with them is that we're establishing a portfolio of projects, and we need to evaluate them and evaluate how much emissions they amount to, how much they take out. So this is what we use eCalc for. Very many ways that you can use other practices also, but through this talk I hope you see there's some strengths in using eCalc for it. We have a big chunk of these reductions are abatement projects. They could be power from shore type projects. We have energy efficiency. That's something that we're very keen on. It's sort of reduced waste, which is reduction in emissions for free, and have obviously good side effects also. Consolidations, that could be taking away an installation which is near its lifetime. And that's other projects also. That could be a sort of a portfolio of other small and large things in there. eCalc, the software itself, as you see this picture. This is a sketch of an offshore installation with some subsurface, some energy, either power from shore, from a wind farm. They can have local power generation. On this installation, they have some processing equipment that requires power to run, and drilling facilities, gas lift. All these data, they're fed into the calculator here. From the top side, from the subsurface, and this calculator then outputs power consumption profiles and emission profiles. That's sort of what the calculator is, where it's relating to the different disciplines, and it's relating to both subsurface and topside and to emissions. So it's integrating these disciplines of facility engineers, subsurface engineers, and climate engineers. And of course, to make this run, you'll have to relate multidisciplinary, and you'll have to have a backing from your management to make this work in reality. How do we convert our plants to power and greenhouse gas emission prognosis? We are having a plan from the reservoir. That's sort of this gray sketch box on the bottom here. Production, volumes and pressures, injection, operational practices in flaring, production efficiency, revision stops, all the plans. They are fed up into the tool. Our topside energy efficiency measures, things that you can do on topside alone, also fed in here. Plans for abatement, electrification projects, consolidation, which is stopping things. That's fed in here, and all these plans are integrated to come up with a power and greenhouse gas emission prognosis. It's done per installation, and then you accumulate those to get a portfolio for all your installations. That's something we typically do after eCalc with, let's say, Power BI or something similar. That's how do we build our capabilities? So we have to do this everywhere. So I have to train a lot of engineers on all our facilities and all our installations. There have to be people that are able to do this. Another picture about how it's done, you will see on the left-hand side here, you'll see a bunch of profiles, reserves profiles, production profiles, or in different types of projects and resource classes. And then we have taken a snapshot here of 18 of our installations, and we're sort of categorized where are we using energy. So we do like 38% on average is used for the export compressors. 20% on average is for the gas injection compressors. 12% on other compressors. Water injection, 12%, seawater lift, 4%, and other stuff, 14%. So we do get a picture of where should we, if we want to make a significant effort, we do have to work with gas export and injection compressors. That's where the bulk of the emissions are. We also do not only reporting, we also do modifications. So we try to model what can we do better, either with new builds, like in this case, we want to evaluate, for this case, should we use one large compressor or two smaller to do the same job? There is evidently a cost element to this, but also an energy element to this. So we design early phase templates for these. About the multidisciplinarity here, eCalc is in the middle of a lot of things. To the left-hand side, you'll see the inputs, again, reservoir inputs, production profiles. We're talking about long-term here, from the start of production until the end of field lifetime. We have injection and pressure profiles. All these are fed into the calculator, but we also do need to model the topside facilities because that's where the energy is used. So we have a description of the facility. We use equipment vendor data. We use our plans for modifications and our operational knowledge of how things are run in practice. In our company, very few people know all of this, so you have to talk to people on the other side of the hall to be able to understand what's going on either side. And this is a workflow with 5 points here. And I'll go through these 5 points with examples as we talk. So, but the main workflow is map out the main energy consumers. We'll look for the gas compressors like we had on this pie chart on the previous slide. We used something called a Sankey diagram, which is something you can Google. It's just a name of a type of energy flow diagram. We do build simplified models of the top side. Generators, turbines, pumps, and compressors mainly. We'll come back to how we do this. These are called energy functions. And for all models, we would like to know how well it's replicating measured data. If you have historic measured data, we try to simulate it and see if it's matching that. For reservoir engineers, this is similar in principle to history matching, but a lot simpler because the models are not distributed in the subsurface. But the principle is the same. And when we are happy with the model quality, we use it for our predictions to create emission forecasts.
It's a webinar. A webinar.
Vinicius, I can't see the chat, so if you're wanting to communicate with me, please break it.
Yeah, I'll let you know. No worries. I'll keep muting the new participants. Sorry for that.
Yes, thank you. Then after we've done all these predictions, we hunt for measures that we look for what we can optimize. And that is potentially easy. There are low-hanging fruits, but also complex if you look at drainage strategy, because then you're easily fiddling with something you can lose money on. So that can be tricky. When you run the calculator, you get out power consumption and emission prognosis, and that's for the whole lifetime. The whole input time window that you're putting in here, you get in predictions for each data point over here. And then in item 5 here, if you're hunting for measures, you're feeding that understanding back and try to modify either your reservoir drainage strategy or your facilities, or both at the same time. This is a manual work process, Nothing is automated there. The eCalc is just this forward model here. Emphasizing again, to make things happen, you have to have your backing from your managers. They are the decision makers, and we need to create decision foundation data for them. We might be like me, a subsurface engineer, or my friends at the other side of the hall, the operations engineer, or floor down the SSU, that's the climate environment engineers, and other people with operational experience, process engineers and operators. And there are a lot of things that you need to work with here to be able to convince people. So it's a lot of multidisciplinary ways that you need to address. So the motivation, eCalc is developed to ease multidisciplinary energy optimization. You have a tool now that allows you to calculate, and you can extract data from it and show figures that is meaningful to colleagues from other disciplines. It is focusing on long-term emissions. So we do look at future modification plans, not only this year, but maybe what we have planned for in 10 years' time, or maybe in 5 years' time, we have a low pressure production project. In 10 years' time, we're looking at the gas blowdown phase. Lifetime assessment, how long is the economic lifetime? That's what we use it for. We do integrate long-term recovery forecasts, that's Reservoir, and facility modifications in the planning there. We evaluate something we call value for carbon. I guess that's a bit of a Norwegian term because we have tax on CO2 emissions. So we evaluate, is your added production or extended lifetime defending itself in view of the added emissions? Because the added emissions are taxed. I don't know if that's the same in your country. It could be in the future. Also about the reputation of the company, that if you want to go for a net zero target in many years ahead, you still have to create plans, because you're going to be measured on your plans and your ability to achieve the goals you set out. In Equinor, we suggest that reservoir engineers are using eCalc as the main people at the helm of the tool. That's mainly because they know the long-term profiles. They are the people that simulate the reservoir model and create 20, 30, 40 years predictions. But it's evident that the topside engineers are very competent in what's on the topside, so they could also be users. In any way that the decisions you make, they need to be integrating both disciplines. eCalc is not an alternative to your standard simulation software. It's only focusing on energy. It is pretty good on modeling the equipment that we model, but the focus is on energy. Unlike if you have a HYSYS or Unisim or other type of model, you're focusing on drying the gas with glycol, you're focusing on stabilizing the oil for export. And if you have a condensate field, you're focusing on a separated process that gives you the highest liquid amount and NGL takeoff. There's a lot of things that eCalc is not doing, but it is pretty good at predicting the energy consumption. One thing which is very efficient is that it evaluates your whole lifetime prediction in one simulation model. So you don't have to have one HYSYS model per time step like the people in process engineering tend to have. So it's much easier to work with. It does something that we call self-optimizing, because it's able to switch on and off equipment, compressors and pumps, depending on your injection and production rates. We'll come back to that. It is using forward models. Because it's only focusing on energy, it's possible to implement in the software a forward model, meaning that it's much more stable and faster than HYSYS and Unisim because they have a lot of loops inside them. So that's more of a sort of a user perspective. We can do simplified process design studies, and we'll come back to that also. So if you're in academia, you'd like to be able to create a facility that's able to compress the gas that you produce from a reservoir. But also inside Equinor, we'd like to have early phase field development studies. How should we and when should we revamp our compressors, for instance? When do we need to buy an extra compressor stage? We can do early studies of that before we go to the vendors to have the detailed studies. Where can you find the software and why? Well, there is a link here. It's on GitHub and this is open source. You can just download it. It's been there for a few months now. It's a special kind of license that you have to agree with. And Equinor doesn't offer any general hosting support or maintenance for externals. This course is, of course, something you can attend right now. But we haven't set out to be able to do general hosting of it. On this GitHub, there is also a user documentation. And why? Well, we wanted to have academia, partners, vendors to understand how we are thinking. Maybe also contribute. There are things, a lot of tasks here which we have not been able to study ourselves, both on the software itself, but also on how we think about the usage. This is what it looks like if you're downloading and installing it. You'll get this. This is from the user documentation, sort of web interface, which you can click on and look at the various keywords and a few examples also. It's written mainly in Python, around 2000 files, a user interface. It is, at least for me, I mainly use this in Unix command line. User manual with examples, and there is no API really. You'll have to communicate this within and output files. How does it look? It's a text file that you write. When you want to run eCalc, you have to prepare the input in a YAML style. That's a text file. YAML is a standard related to HTML. And there is a link here, you can read about it. The reason for this is that eCalc is written in Python and it uses a YAML loader package. That's from an external repo somewhere that we just included and used that to read YAML files. So for that to work, you'll have to follow the YAML standard, which you can read about here. It's quite picky about technical details. eCalc loads this YAML file using this YAML loader. Then inside it does calculations and writes an output file that you can view with another viewer. Either on Unix or you can view it with Excel or something. Inside eCalc, there are 6 sections. They are listed here. There is a section where you put in your time series data. That's your production profile typically, precious rates, either history or predictions. These have to be in SI units, rates in standard cubes per day. Pressures in bar, atmosphere, bar. Power will be reported in megawatts. Facility inputs. That's your models of your topside. That's generator sets, water injection pumps, and other equipment. A special section about compressors, because compressors work with gas, which is a fluid that's compressible. So here you need to do some PVT calculations, some thermodynamics, and that's going on. So you're setting that up here, and then you describe your fluids, compressor charge, trains, and turbines. We'll come back to that, spend some time on that. There's a special section called variables where you can write expressions to make your code more efficient and readable. You have to define what kind of fuel you're running on. If you're burning natural gas, you have to write how much CO2 content it has, etc. If you're using diesel, there is another CO2 content in that, the energy content in the fuel, really. And then the main section is where you actually describe your installation. And you can have more than one in the same file. So this is an example that some of you probably recognize. This is usually the longest section. That's where you set up your pumps, your compressors, and all the equipment. I'll come back to that. We'll look at the time series part here. Time series input in eCalc. Well, you see something you can recognize here, a date, a lot of dates here. Production efficiency, some numbers, field oil production rate or an oil rate, gas sales rate, seawater injection rate, field gas injection rate, field gas lift injection rate, produced water injection rate, whatever. You can choose whatever name you want here. That's a typical time series. This is just a syntax that you can read in the manual about these things in the orange boxes. You're not limited to one file. You can have as many as you like. But we do recommend that you shouldn't have pressure and rate in the same file because they should be interpolated differently. Reservoir engineers, they are quite familiar with rate being left, that is backwards filling. That's common with the reservoir simulators, but if you have something else, you have to specify the interpolation type as an option here. You can put in pressures, however, they're often linear. So that's technicalities that can run into the functionality to handle that. In addition to having dates in the time series input here, in the installation sections, you can actually write dates to change your compressor train at a specific date, for instance, or add a new profile or whatever you would like to do. So it's quite flexible with respect to that. Production efficiency is dimensionless. All rate data should be in standard cube per calendar day rate if you provide regularity. PE is regularity. And you can look at the documentation also. This is a topic I mentioned specifically because people often make mistakes with respect to regularity. Not only eCalc engineers, but also many reservoir engineers. It's an important topic. Here is how eCalc does it. It takes from the time series, you can take a PE varying with time, or if you don't want to have it varying with time, you can just put in this constant number. And then eCalc, if you specify this, it treats all rates as calendar day rates. You can do, this is how you do it here. You're in your installation, let's say it's P52, you write regularity. This could be a number or a reference to a file which you have put in the time series part. Then this figure explains what's in the text here. Inside eCalc, it converts all rates to stream day rates before energy calculations are performed. That's what you do here, to divide by regularity. Inside the models, you calculate power consumption with rates in stream day rates. Important for two things. It's similar to what you do with the reservoir simulations. You'll have an efficiency there that sort of makes sure that your cumulative outtake is correct and honoring your downtime of the facility. But pressure losses in wells and pipelines, they need to be evaluated with the physical rates. Likewise here, the power consumption in the pump, it needs to be evaluated using your daily stream day rate, because otherwise you'll potentially underestimate your power consumption, and potentially you will be missing that the model itself, the pump itself, has a capacity limitation, which is defined in stream day rates. After you've done that, you sum the power from all your pumps and other equipments into this genset, which is the generator set. We'll come back to that. That converts power consumption into fuel consumption, still in stream day rates. And then you multiply by regularity again to arrive at fuel consumption in calendar day rates. Quite simple, but often misunderstood. Time intervals in eCalc. Time series, that's the files that we looked at. They can have all the time-dependent inputs. eCalc in addition allows scheduling changes at given dates. Like here as an example, you can specify your hydrocarbon export at dates that from this date, year 2001, January 1st. It's a reference to a file called sim1. It's your oil production. But from year 2005, January 1st, you start gas sales in addition, and you have to add that. Just in this illustration of how you can use dates in the installation section to model changes. If no date is given, data is used throughout the whole prediction without any changes. So if you didn't write a date here, you just put sim1 oil production would apply to the whole time window from start to end. This approach to dates can be used for all the consumers in the time series sections. So in the installation section, you should state here. This here as a note that we'll come back to, that we have something we call generic compressor models, and they need specific caution. We'll look at that later. Next main section. These are the top level topics: the workflow, CO2 emissions, and intensity. So here on the left-hand side, when you see these black slides with the black part to the left, they are showing that we're talking about a specific step in the workflow that I showed earlier on. And here it's wiped out. We map the energy consumers. What we do here is we create a Sankey diagram, and we use that to identify the significant equipment. Here is an illustration of a Sankey diagram. It's an energy flow diagram with different colors. It shows equipment also. So the equipment here is a legend down here. You see T for turbine, C for compressor, G for generator, P for pump, and for miscellaneous. And there are some arrows here with different colors. These orange ones, they are the fuel rates. And you see the thickness of the arrows, that indicates how much fuel you're using per equipment. So this plus this plus this plus this should be equal to this. Over here you have electric energy in blue-gray color. So here you see there are two generators that creates electric power. That's showing how you're creating electric power on your installation. You're putting fuel into a turbine. There is a mechanical shaft. On the shaft, you mount a generator, and when you burn fuel, the shaft is rotating, the generator is rotating, and that can create electric energy. And that electric energy is used in consumers over here. C for a compressor. This is a thick arrow, so this uses a lot of electric energy. This is two compressors on the same shaft with a black rod between them. That's the shaft. This is also quite thick, so I think that's consuming a lot of energy. And there is some P, that's a pump, two of A. And there is a thin arrow here with a P. And you see these P's, they have the red dotted line around them saying it's a big consumer. We'd like to model that. This one here is probably a utility pump. Well, we could model it, but let's save some time and just lump it as a fixed number, for instance, or an on-off load, something simple. Same with other equipment. Miscellaneous could be heating, could be a lot of small equipment. That's your cafeteria, your lighting, your whatever. A lot of things could be here. Things that are modeled in eCalc, we put a dotted line around on these diagrams. We model these compressors, these pumps, but not these P's and M's. We are not neglecting them, we're just saying they're fixed, so we assign a constant number to them. And over here, these are with a dashed line around, they are the turbines. That's where you really burn fuel, and that's where you create your emissions, which is not drawn here. Actually, this orange arrow here should be a lot thicker than this greenish line here, because here is a lot of waste. When you burn fuel, you will have exhaust, and exhaust is hot, so you lose energy in the exhaust. So these are important to model. And also down here, you'll have a turbine with a shaft that runs compressors directly. Over here, you have a turbine driving a generator that drives a compressor train, and these have electric motors, which is not drawn here. But here you can, this is more common situation for large compressors. You have a turbine with compressors mounted directly on its shaft. Instead of a G, you have C. In this case, you have 3 compressor stages at the same shaft, meaning that there are 3 compressor stages which rotates on the same speed. Obviously, flaring can also be added. There's nothing to model. We just integrate it into the complete report. You typically include a lot of other things like that. You typically include methane, non-methane volatile oil components. You can include other emission sources, NOx, whatever you'd like to put in here can be reported. It's not so hard to make this diagram. And it's not so important for you that you draw the right thicknesses here. Evidently, this is a snapshot in time. It is important that you understand the concept, because we use this to select what we model. If you go on in the workflow, now the Sanka diagram was used to map energy consumers. This is energy flows. A process flow diagram doesn't show energy flow, it shows where the fluids are flowing, but the reservoir fluid is showing. Well streams are coming into a separator. At the separator conditions, you split the phases. Gas off on the top, oil off in the middle, water off in the bottom. Water is treated and maybe re-injected or dumped to sea. These separators, they are typically not at atmospheric pressure. Typically for an oil field, 15 bar, for a gas field, 70 bar. You take it down in stages here to maximize your liquid recovery. So you'll have in this picture 3 separated stages. At the outlet here, and where you have a cooler, you have the oil export at stabilized oil at the atmospheric pressure. That you can put into a tanker and ship to the refineries. And all the gases from the top of each of these is collected. And this one is at atmospheric pressure. This one might be at 15 bars. This one might be at 7 bars. To take this gas, well, for flaring, it's emissions. We probably would like to get rid of that, so we have to collect it. We compress it. First, we cool, put in a scrubber. We'll take off a little bit of liquid, which is put back in here. Oh, sorry. And then the gas is going into a compressor, going into a new cooler, a new scrubber. Liquid is collected. Gas is then compressed up to this here. Now it's at 7 bars. Now you can mix it with this gas. That gas is cooled, scrubber, you take off the liquid again back here. This gas is now at 15 bars, you can mix it with this gas. Then you put that gas into another cooler. This is where the main gas rate is, of course. The inlet separator is where you take off the most of the gas. That gas is into a scrubber, and you have some glycol treatment here to remove water. You typically you would not like to have water in your gas export. Then you take off some fuel gas. That's where you get your fuel gas for your turbines from. Somewhere, in this case, it's actually a dried version of what you take off of your inlet separator, but other installations can have a different fuel gas offtake. This is then burnt to make the turbines go around. Then you put the gas into a compressor. This is 2 stages with cooler, scrubber, compressor, cooler, and then you do gas export or gas injection. So if you relate to the Sankey diagram, what do we think we need to model here? Well, the water injection pump is probably quite big, so this one we'd like to make a model of. We might have several in parallel. These ones, well, we could model them, but typically the gas rates from the 2nd and 3rd stage separators, they are quite small, so we tend to avoid modeling them. These 3 in the green box here, and there's another reason for that. The reservoir engineers, they can tell you the gas rate from the total up here, the total gas export, but they can't tell you the gas rate here and here. For that, you need a process simulation model. If you have that, use it. eCalc isn't picky about where the rates are coming from, but you have to know these rates. So typically, we don't know them. Luckily, the energy consumption is low because the rate is low. For sure, the pressures are not varying. 1 bar, 7 bar, 15 bar throughout the lifetime. So it's at best a relation between rate and power. It's not pressure dependent. So by saying these are fixed or maybe only rate dependent, it's a fairly good approximation. But up here, these compressors we like to model. These are the ones that are typically turbine driven. These, the ones in the green, are typically electrically driven. They are typically on the same shaft. That could happen here as well. So these ones we model, this TEG system. There are some utility pumps around pumping the TEG around the glycol, but we don't model them. They are small energy consumers and not varying a lot. So eCalc, we typically focus on the big things. After all, we are dealing with the reservoir profiles which are kind of uncertain in the future. So making an informed assumption about small utility systems is defendable. So we use this again to understand how to set up the installation model. The previous diagram was to understand what to model. Here we understand how to connect them. We'll show you a picture of what a turbine is. This is what you use to create rotational energy, which you can use to create electric power with a generator or directly to run compressors. This is a picture from a vendor, LM2500 from GE. This is a picture that just shows you that it's actually quite complex equipment. I'm not going to spend time on explaining how this works, but basically it is using natural gas. But as you saw at the previous slide, that natural gas is not at atmospheric pressure, and it doesn't contain oxygen, so it won't burn. So you have to mix it with oxygen, and oxygen is taken from the surroundings at atmospheric pressure. So there's a pre-compressor stage here, which actually only increases the pressure of the oxygen up to your fuel pressure. Then you can mix them and ignite them. And when you burn gas, it expands. So that creates movement. And by the shaping of the internals of this one, it is creating rotational force. That creates a rotational force on the outlet side here and many small blade stages out here. And you're taking off outside here the rotational force on the shaft. And that rotational force is actually also rotating the oxygen intake part. So it's creating its own pre-compressor for oxygen here. A lot of measurements, lubrication systems. This is a very hard equipment to have problem with, so that's why we use GE LM 2500. It's very stable, doesn't break, can run for years. It is not very efficient though. Most of the energy is lost in the exhaust. About 2/3 of the energy that you burn in the fuel here is lost as exhaust, which didn't used to be a problem. We had a lot of this gas, but if you want to reduce emissions, it's in the exhaust that the CO2 is contained. So if you want to do something about this to increase the efficiency, you'll actually have to take out the energy in the exhaust. Typically easy to do onshore, but the exhaust, it's only heat. It's low quality energy, so you need a huge equipment to be able to take it out. And offshore, typically weight and space constrained, can be quite hard, but there are attempts to do that. You can put a steam facility in the exhaust pipeline and you use a steam circuit to create additional electric energy and increase the overall efficiency of the system. Just so you can sort of recognize the numbers, for one of these to be in operation, typically look at around 100,000 tons per year of these. Big emitter. That varies a lot from installation to installation, of course, but this just to give you a hunch about the size of things here. Over to compressors. This is just a sketch. You up in the corner, I put, from the Sankey diagram, a turbine with a shaft and 3 stages. Here you see the 3 compressor stages with a shaft. What is your problem then? Well, the reservoir engineers, they do know a lot about this thing here. It's a model of the reservoir with a lot of wells and, production, injection, pressures, all these things, they're well known to them. They produce that out, and they probably have some injection of the gas maybe in here. That gas, well, they put it into the well, into the separator, but that separator isn't at the export of injection pressure that you need, so you have to compress it. In this case, in 3 stages. The reason that you're having several stages, we'll come back to that, but it has to do with that when you're doing compression, you're actually doing something thermodynamical. And that increases not only the pressure, but the temperature on the outlet. And the temperature is typically a problem because the flanges, the steel quality on the downstream side here, can't take temperatures above, let's say 140, 50 degrees. So at a certain pressure ratio, you have to cool it before you put it into the next one. That's what we had on the sketches earlier on. Well, your rate and pressure goes in here and your injection pressure down here. But to make this actually rotate, you need to have a force. And that's what the turbine is doing. That large equipment on the previous slide, you burn fuel, it creates torque. And on the shaft that you mount, that's sort of varying here. That's this curvy arrow showing. Well, you need to know how much power do you need, because that evidently changes with your gas rate and your pressure and the pressure you need or ask for out here. So that is something that the reservoir engineer is actually having a say on. If you want to reduce your emissions, can you do something with your injection pressure? But need to be able to calculate that then. How much power do you need to rotate this shaft? That's what eCalc does for you, calculate that power. Then you've done the hard part. The next is, well, if you know how much power you need on the shaft, then it's easy to calculate how much fuel this turbine is using. Fairly easy. Cheating a bit here. Well, say you're able to calculate the power, then you can look up how much fuel the turbine needs to create that power. When you know the fuel rate, then it's really easy to calculate the emissions, your CO2, your NOx, your methane. So that's all that you have to do. This is an integrated picture of what eCalc does with compressors. And it does this because it's a compressible fluid here, so you need to do this thermodynamics to be able to do this. With water injection, it's much simpler. Water is not compressible. Well, this is what it does with the compressor train with 3 stages and a turbine. And then all these things are then modeled similarly. This is a bookkeeping side of eCalc. So you put into eCalc again your injection rates and pressures, your production efficiency, and then you categorize things. Something is gas turbine drive, like the gas injection compressor from the previous slide. You can have gas export compressors, you can have recompression, the stuff in the green box and neglected. Water injection pumps can have turbine drive, quite seldom though. A lot of equipment also have electric motors. So your gas export compressors, they can be electric motor driven. Your injection compressors, your water injection pumps typically have electric motor. Recompressors typically have electric motor. Export oil pumps, these are electric drives. You also model these. You have other loads like things that are just on-off loads or things we don't model. We put them in here as a constant number, constant load. And we have flaring, low pressure, high pressure, venting. This is just something we put in as a file with the time data in, and we just sum it all. These things that are consuming power from these boxes, we get their power consumption. We sum that into the generator set, and the generator set. All the many generators you have on your installation, we sum them all and we calculate how much fuel they use. So then we have fuel from this blue box here, fuel from this blue box, fuel from this blue box, sum it all. And we can have different fuels for different equipments. So you just need to put it up in the right setting, and then you sum it and you calculate your CO2 emissions. So that's the bookkeeping part of it. You could do all this in Excel, at least for your summing and reporting, but compressor models and having several of the water injection pumps is a bit cumbersome in other tools. Then over to emissions. It's easy to calculate. It's a formula here. You sum all the fuel rates, you had that in the previous picture, and you calculate the CO2 emissions. How do you do that? You have the fuel rate in standard cube per day, and you have a CO2 factor in kilo per standard cube. If you multiply this, you will see that you have kilo per day. If you divide by 1,000, you have tons per day. This is simple. How do you get that CO2 factor? This is a property of your fuel. Typically in this range here, 2 to 2.6 kilo per standard cubic, but it varies with your fuel gas composition. So your topside people, they will be able to tell you this, or you can calculate it. Actually, it's a formula that you can calculate if you have the methane, CO2, methane, etc. properties. And these numbers here, the 2.6 kilo per standard cube, they are defined in this fuel type section that I mentioned in the AO. That's just a syntax part. Includes some other things also. You can have definitions of methane, non-methane, NOx, diesel, different. You can have many different fuel types. There is a topic which is used a lot in academia and used to be used in the industry earlier also. It's CO2 intensity. The initial slide I had talked about absolute emissions. Why aren't we talking about intensity in the industry? This section here is a few slides about intensity. Petoro is rewriting the definition. That's a Norwegian authority. That's the owner of the Norwegian oil fields in Norway. So, but they wrote in their annual report a definition which I translated into English here. Emission intensity, the ratio between emissions and production, in detail emissions per produced volume of goods or services over time. Viewing emission intensity over time provides an indicator showing if the production has become more or less emission intensive. So it's the ratio here, CO2 intensity is measured in kilo CO2 per barrel oil equivalents. It's the ratio total scope 1 CO2 emissions in kilo by the total net production in barrel oil equivalents. Net production meaning what you sell. So if you're not selling all your gas, you're producing a lot more gas. For instance, you're injecting, and below the denominator, it's the sales gas plus your oil that you're selling. Scope 1 emissions is what you actually are burning of fuels and emitting CO2 on your installation. So in installation A, if you're emitting 100,000 tons CO2 per year, then you put a CO2 emissions that you actually create yourself here. But this needs to be integrated over time. And then it's a question about which time interval. So we have created two variants in the output for you. One that looks at all the time horizon from start of production until this point in time. Or you can have something which is more like a rolling horizon. It measures from January to December 31st for each individual year. So what does this look like? Just an example. First, over all times from start of production until now in the green one. It is a much smoother line. The orange line is the yearly one, which is constant in each year here. And you see, for some reason, they tend to be much higher towards the end here. The reason is that you only measure the production in this year here. That towards the tail, you assume or you know that the production is quite low. And your energy consumption, your gas compression is probably fairly high still. So this is why the stuff below in the ratio is becoming lower and lower than while the stuff on the top of the ratio is fairly constant. So this will increase over time. But for the green line, you're downweighted by a lot of production in the early years. You had a lot of oil production early on. So even though you have a low intensity here now, it's sort of benefiting from that early production. This is nice to show to, let's say, our peers in the authorities or media, but it's very hard to change. So yeah, if you have any CO2 emission reduction measures here, well, you're barely going to change the green line here because it's so dominated by the early stuff. On the other hand, the orange here, it's easy to change because you're only operating within, measuring within 1 year. But it's a ratio in any way. So these are the two variants you'll have. So intensity is a fraction or ratio. Reducing intensity can be achieved by increasing production. So increasing production, well, it doesn't necessarily reduce our emissions. So if you want to have a real ambition, you should be measured on your absolute emissions and not your relative emissions, your ratio. So improving efficiency in a well, for instance, probably won't reduce your emissions. So, last slide about that, reducing emissions versus CO2 intensity. You've seen this picture before. Most installations are capacity constrained topside. Improving efficiency in a single well by reducing unwanted phase will be compensated by increasing production from other wells to refill the capacity. If you're filling your gas train here that can't handle more gas, that's your capacity constraint. if you're doing something smart with the well out here to reduce gas, put in a smart completion, well, they have a lot of well potential, so they will just turn up another well to continue filling this train. They produce more oil, but they're not reducing emissions. So improving efficiency in the well will likely not reduce emissions. But of course, value is, in this example, good. Since the intensity is a fraction, reducing intensity can be achieved by increasing production. How do we know that? That's why Equinor has set absolute emission reduction goals. Now I've done all the introductory stuff. It's this next part, and I think, Vinicius, that we should have a break now, talk about an hour.
Yeah, it seems like a good idea. You have to drink some water. And then I can summarize the questions. We do have two questions here, and then we can address them right after the break. So
Okay.
how long should that be enough? 10 minutes, 5 to 10 minutes. Is that okay?
And Vinicius, do you want me
Yeah.
to continue another hour now, or is it in conflict with the rest of your
Yeah, our
course?
current plan is if we can go into 12:40, which is 40 minutes additional from now. It could be great if you could keep this.
No problem for me.
That'll
Just
be half
tell
an
me
hour
when I need
additional.
to go home.
Yeah. No, if you can stay half an hour after the break, Stu, if that's okay for you. So 10 minutes break plus half an hour. Is that sounds okay?
Yeah, and the questions let's have a look
Yeah,
at
there's
that.
2 questions from Basay. So first one is, can flow assurance simulations be integrated with eCalc for fluid life studies? That's the first one. So regarding some flow assurance and integration.
Yeah.
And how that would affect the.
Oh, that's an interesting question.
Yeah.
That needs to be discussed. eCalc can use a lot of data, but flow assurance here, then that's a quite large topic.
Yeah.
There are a lot of things upstream here, which I guess you know about, Vinicius, which are a bit complex. And are they consistent? So I'll probably like to answer that as no. You'll have to do flow assurance simulations. You can integrate the tools, yes, but flow assurance stands as its own discipline.
It's not part of the modeling that you would expect to have components of different potential issues that
It's like a
would lead.
sequence of jobs. You can run the flow assurance simulations and use the output from that as input to eCalc. But it all depends on the user here, how sensible he is doing it.
And running different scenarios as well for different risk that is estimated for flow assurance risk, right? So another question also from Basay is for the output part of the workflow. Does eCalc have a provision for determination of soot generation and flare emissions, especially when where wet gas is handled? So regarding how we model flare and if it can produce any estimation on soot generation.
We haven't done that. I'm not sure, Hedda, do you listen here? Can we incorporate soot as a property of the fuels?
We haven't done it yet, at least not to my knowledge. Usually we just use the emission factor, as you know, Frode, for the flare.
I don't know if that may be something possible, having the composition of what is being flared have additional function to output this type of thing, but maybe that's not yet defined in the models that we have in eCalc. So that should be.
I don't think so. We haven't thought
answer.
about the
Yeah.
suit.
So that maybe if anyone else have any other question regarding the first part that you have presented, please either raise your hand and open your mic, or write it down in the chat. So let's maybe go for a break through that. So and then we can address the questions that people would write in the chat.
Yeah. Mm-hmm.
And 10 minutes sounds okay.
Good for me.
Okay, so see you guys in 10 minutes, 12:17, to try to keep up with time here. Thanks again for the first part. See you guys in 10 minutes.